like where that story went. I thought you said you melted it by accident. I thought that's where that story was going.
Oh, we've melted plenty of other things.
All right, when you have a 6,000 degree process, yeah, you
Yes.
melt a few things along the way while you optimize that hardware.
Welcome to the first episode of Critical Material Production with Plasma, a new mini-series from MANSUS and 6K. I'm the host of the series, Jim Woodcock, and over the next 3 episodes, we'll be taking a deeper dive into 6K Inc., including their microwave plasma material production platform, or Unimelt. We'll be looking at the science of plasma, the power of partnerships, and some of the challenges and opportunities associated with building an entirely new production facility from scratch. 6K is first and foremost an advanced materials development and production company, but it has sustainability right at its heart. Through its proprietary Unimelt platform, the company is able to produce a vast array of materials, often materials that are hard or even impossible to process by traditional means. And it does so more quickly and with a fraction of the environmental footprint of traditional methods. The company operates in 3 distinct areas, through 6K Additive, 6K Energy, and 6K Next. 6K Additive uses the Unimelt platform to produce metal powders for additive manufacturing. The flexibility of the microwave plasma system means that the Unimelt can process common or garden AM metals, as well as hard-to-process metals and alloys, including refractories. Whatever the material produced, the system makes high-density, highly spheroidized powder within the powder size distribution required, and with minimal waste when compared to, for example, a traditional gas atomization system. The 6K Energy part of the business is focused on deploying the Unimelt in the energy market, specifically battery materials across a range of battery chemistries. The Unimelt platform enables the production of high-quality cathode and anode materials, for example those used in lithium-ion batteries, and it allows a precise control over the material properties such as the particle size, phase purity, and the morphology, and these are crucial elements for battery performance. Finally, 6K Next is an internal incubator that seeks out novel uses for the Unimelt platform. One of those applications recently released is the destruction of PFAS materials. However, in this episode, I'm going to be speaking with Saurabh Ullal, he is the CEO at 6K Inc., Mike Kozlowski, who is the R&D Director at 6K Inc., and Greg Wrobel, who is Technical Program Manager at 6K Energy. In the discussion, the team talks about what plasma is, how it's harnessed in the Unimelt platform, and what the implications are across the different business units. We also hear about the journey of taking the Unimelt from a concept and a research program in university right through to commercialization, and that's a story that includes some pretty incredible feats of human strength and some pretty hair-raising moments too. To begin, I asked Saurabh to start really from basics. What exactly is plasma, and what makes it so special?
So the plasma is commonly referred to as the fourth state of matter. It's a collection of ionized and activated species along with high temperature gases, not unlike what happens on the surface of the sun that allows the sun to generate the heat and deliver the light to our planet. So that's the state of matter, which is what the plasma is.
And just a quick one, sorry to interrupt. A species. Yeah. What is a species in that terminology? Because normally we think of a species as being maybe a separate division of an organism.
Absolutely. So thanks for correcting me, Jim. Think about it as like a gas molecule, like a molecule of nitrogen or a molecule of oxygen that's in the atmosphere. That's one type of species. In addition to those gas molecules, we have ionized species, free electrons, activated species of those same gas molecules and gas atoms. And that collection of species, it's the soup, the plasma soup that's all mixed together. And what makes this plasma soup really unique is its energetic nature allows us to play some tricks that help drive some conversions, drive some reactions that could otherwise not occur, or could not occur within the time scale that we would want them to occur.
Okay. So, and how is just in relatively simple terms, I guess, at the moment, how do you create that plasma then? How do you get to this fourth state from where you start?
Right. So the way we at 6K generate that plasma is through the use of microwave energy. Now, not that different from what you have in your homes, as a microwave oven. In a microwave oven, the microwave energy is taken and converted into heat. In your microwave oven, that microwave energy couples with the water or any liquid that's in your food or in your cup of tea, caffeinated or decaffeinated, and generates that heat. We leverage that same principle to a higher degree and take that microwave energy and couple it with gases and generate an extreme amount of heat by forming the plasma, that fourth state of matter, that soup. And it's really what we bring to the table in our ability to take that microwave energy and controllably convert it into the plasma that we then utilize to really create a variety of products that differentiates us from the others.
So is it the same? Is it literally the same microwaves as a microwave oven? Is it just the intensity and frequency that's different?
That's exactly right, Jim. Typical home microwave ovens are operating about 1,000 watts, 1,500 watts. What we use are larger microwave generators. Think about a microwave system that's the size of your refrigerator. And those typically go up to powers as high as 100 kilowatts or 100,000 watts. And that's what allows us to generate the plasma and the temperatures that we desire, right? Temperatures as high as 6,000 degrees, which directly goes into 6K. That's our name, right? 6,000 degrees is the temperature of the plasma that we create.
Okay, so if I've ever got a really cold cup of decaffeinated tea, then second two in there and it'll be entirely gone.
Exactly.
And I can get some caffeine. That's my excuse to go back to caffeinated beverages. So these things never just happen overnight, and they never happen by accident. So, Greg, could you give us a little insight maybe into the evolution of how we ended up with what we see now? If we go to your production facilities, you can go into the bays, you can see a unimelt. How did we get from concept theory to that?
Sure. Yeah. Thanks, Jim. It's excuse me. I have a little bit of a cold today, so you'll hear the stuffiness in my voice. But it started as a technology incubator at the University of Connecticut, where our founder and co-founder had toiled in a lab for 7 years, just trying to bring the idea of this plasma from a concept into something that we can use for producing materials. And they put an incredible amount of time and energy into that work. By the time I had joined, around the time I was finishing up my PhD there in material science and engineering, they had a fairly well-established prototype process. And I had jumped in working on a Department of Defense grant project they had been working on, developing thermal barrier coatings, which they use in jet engines to protect the metal parts from the high heat. This would be the next generation of thermal barrier coating that would basically have jet engines have better fuel efficiency, so more gas mileage out of your airplane. And that's where it all started. So they had thought of this amazing plasma concept for making materials in this way that no one else had made before. And for me, it was amazing coming out of material science and engineering, this way of making materials that was completely unconventional, turning a liquid chemical feedstock into material powder in a fraction of a second. I mean, it was a playground, and the early work had started as finding the right application for this plasma. We know there was utility for it for a unique process, and it was a matter of finding the right materials and the funding to make the right materials. So a lot of time had been spent scouring through literature, a lot of grants out there, right from the Department of Energy and the Department of Defense. And so when I had joined, just a lot of work combing through the solicitations from the various organizations and finding, areas to be able to get some money to demonstrate this process. And yeah, so I could get into a deeper history, or I'm not sure what you want to do next with questions. So I'll hand it back to you for a second there, Jim, to guide where you want to go with that.
Well, and we can kind of link the two first bits, I guess. Well, I was amazed that they were researching in a lab for 7 years before anything happened. I mean, I started off, my degree was in pharmacology, and I always thought I was going to go and be a drug researcher and go and work for Pfizer or Glaxo or something. But then going through my degree and realizing I could just be in a lab for the rest of my life researching something only to find in 35 years that, it didn't work. And I don't know whether I could have personally dealt with that.
It takes a certain kind of person to be able to sit in a lab like that for such a long time, just trying to prove out one thing. Yes.
And you've got to be fairly confident that, what you're trying to prove is provable and viable at the end of it. I guess there's a certain leap of faith there. But yeah, I was just going to ask, Mike, I believe you have been more involved in the torch development, which is the actual plasma torch that we're talking about. So how did that come up? How did that tie into the story, I guess? Was that work that happened after the initial research kind of towards commercialization, or did that happen around the same time, or what was that like?
Yeah, I think it was an evolution from kind of the initial feasibility that Greg mentioned the early team was working on. So they had a torch system, which is basically where the plasma gets generated. They had a system that was working for them at the time to show these early pieces of feasibility with the technology. When I joined, there was a push to sort of mature that, make sure it was very reliable, increase the amount of power handling that it could achieve. So early days, it was me working on it as a designer, and as I've kind of grown in the company, we formed a team to really push the boundaries of what the torch and subsequently the plasma system can do. So now, instead of just focusing on the torch itself, where kind of the flame comes out, we focus on that whole subsystem of plasma, right? So it's from the microwave generator all the way through into how those microwaves or that power is coupling with the gas and forming the plasma.
And so what is happening in there in the production of a material? What are the physical chemical processes from that actually occur within the Unimelt? So what goes in, what happens to it, and what comes out?
I think it depends on the application, right? Whether it's metal powder or it's the energy process with the liquid spray. But essentially, in some cases, we're leveraging the thermal power sort of the plasma. And in other cases, we're leveraging more of the chemical nature in some of the future work that we're doing. The cool thing about it is, we have this platform technology where the heart of it is very similar, and we're deploying it across different business units.
Yeah, maybe I can come at it slightly differently. And there's two different aspects of what allows us to be successful. The first aspect, as I'd mentioned previously, was the creation of that plasma, right? As you can imagine, and for those of you who've seen, YouTube videos or articles on, hey, what are the processes occurring on the surface of the sun? It's incredibly chaotic. To some of us, it may be controlled chaos, but it is incredibly chaotic. So the first order of business when you are taking that microwave energy and creating that plasma is how do you literally control that chaos, right? And to that end, Mike alluded to the fact that we now have a team set up, and we've had a team set up, for the past 6-7 years that really work on how you can harness that chaos and use it to our benefit. Right? So that's the first step, is how do you take that chaotic process of creating a plasma and make it a controlled, predictable outcome. Step 2 is, now that you have that controlled outcome, in this case, using the plasma to create a very uniform high temperature processing zone, the second step now involves how do you use that processing zone to our benefit. And that benefit is unlocked by feeding various materials, starting materials, feedstocks, precursors. You'll hear us using these terms interchangeably. And whether those precursors are solid, liquid, or gas, that's the input. As those inputs go through that controlled high temperature plasma zone, they make products that are useful. Now, engineered products that have undergone either a physical or a chemical transition in the high temperature plasma zone to yield that finished product that our customers are looking for. So it's really a two-stepper of how you first harness that chaos to create something that's controlled, and then you use that controlled outcome to create the products that you're looking for.
Yeah, and I'll
So
jump in.
it's
I like to. Sometimes it's nice to visualize things in a simple manner. And one of the ways we used to visualize things early on is, when it comes to processing this precursor, this feedstock, there's a couple of ways we can do it, many ways. The two dominant ones are starting with a liquid chemical feedstock. So essentially liquid or water with dissolved metallic salts or dissolved chemicals go into plasma, water evaporates, and there's a reaction with the plasma gases, and then out the other side, after all the water is evaporated, you have that reaction, comes material powder in whatever form you want. The other is you input metal powder, which we're doing with the additive manufacturing. Metal powder of small size goes through plasma and melts and forms into a sphere, just like a drop of water falling through air. And so in that case, it's just melting powder, turning into a sphere. None of the particles touch. They come out the other side as spheroidized metal powders.
Okay, and that I think that takes us into a good direction, because you mentioned the additive side, and as I introduced you, you're on the energy side of the business. So there are these two current sides to 6K. How did you get from the research and the 7 years in a lab and blah 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 to you have a product, but now look at you, you're all there with your branded fleeces on, and again, these things don't happen, by chance. What was the story around the formation of 6K as a kind of as a company as it is today, and then those two separate divisions that we talk about most, and maybe will there be more? What are the plans there? So
yeah, so I'll continue on from where I had left off when I was first describing how we had come to what we are. So as we were exploring those grants, we come across a bunch of different types of materials, and there's always this balance between, is there a large market for it? Can we make money from it? Is it something sustainable, right? We're in that age where we want to better the world. We don't just want to be making something to make something just to make money. And so we had looked at things, there are a lot of stuff for the Department of Defense. Other things would be, transparent ceramics for missile domes. This was around the time, this was long ago, when LEDs were first coming to market. So we explored the phosphor materials, as they call it, that absorb or turn the blue light from the LED into the light we all are, the light color that's illuminating our rooms right now. And then out came a grant for battery materials. And so now we're really excited about this one, right? It's a huge market. Electric vehicles are taking over, grid storage, mobile devices. And on top of it, the market, so it's sustainable and the market's huge. And so we applied for this grant and we get it. And so that kicks off our first work in battery materials. And it turns out that our plasma process has a makes a battery material in a way that no others can do it and gives a unique material property. So after many years of R&D, going through a phase 1 and a phase 2 of this grant, we learned that we have enabled a process for making battery materials that's cost effective so that we can make it in the United States while it's made overseas. So now energy security in the United States, it's sustainable, and it's allowing us to shorten the time to make it, so less energy, less CO2 use or less gas usage. Just it's a sustainable process to make a sustainable product. And so that's where battery materials had come into. And our CEO and executive team really jumped on this one and helped guide our focus to form what is now 6K Energy. And so that's where the battery materials has come from. Additive, we had also explored. We know that our competitors will using thermal processes to sphericize materials, but they were having challenges. Their process was too hot. And so we knew that this was a big market for us again, right? Because we want to make sure that we're hitting something that can make us money, but there was also a sustainability aspect. And after some thinking, we thought of turning old scrap metal shavings from machine shops into sphericized metal to add that sustainability aspect to it. And after doing some early proof of concept work with the team here, we realized that this process is suited for that, well suited for sphericizing materials while overcoming some of the challenges that our incumbent processes had. And so again, the executive team really jumped on that, saw the market opportunity, the sustainability opportunity, and broke off with 6K Additive. And that's where essentially you get 6K Additive and 6K Energy now.
And obviously additive is my background, and I appreciate how important metal additive manufacturing is. It's always touted to be going to be very important, and then there's these hurdles that are in the way, and some of them are just physics. You can't really get around the physics of some of the processes. They're always going to be what they are. But yeah, a lot of the more interesting applications are hampered by not having the materials, especially like you say in defence, aerospace, etc., because they've traditionally been incredibly hard to process. And even when they can be processed, the way that they are made is inefficient in terms of what you put into what you get out, especially if you don't have the right sizes, powder sizes, too big a distribution. So what could come next then? So is there anything on the table that you think, obviously additive, you've seen the potential for the battery materials, which like you say is huge and is very on topic for the moment. What next? Because it seems like it's a very flexible platform. I imagine, as we sit here today, there are things that can be done with the Unibelt that you do not know yet.
Yes, so I'm glad you used the word platform, Jim, because that's exactly how we think about it, which is we have this technology that we can leverage and apply in multiple different market segments. As Greg pointed out, the additive and energy segments are the first two forays of using this plasma technology. There are other ideas that we are working on concertedly, and we've actually created a small group within 6K, very innovatively named 6K Next, which essentially describes what we're looking at, which is how do we use our platform for the next opportunities that are coming up. Mm-hmm. Some of these opportunities are related to how we create carbon-containing products by leveraging clean sources of carbon. The cleanest source of carbon is CO2, and convert that CO2 into valuable carbon products, whether it be carbon nanotubes, whether it be various forms of graphene, all of which are engineered to provide our customers the value that they're looking for. Mm-hmm. And if you pull at that thread, especially within the additive market, of how we are taking scrap material that would otherwise be going to landfill, and converting it into valuable product. We're using that same mentality, taking CO2, which we all know is a lot more of getting generated than we can actually consume, and finding a way using our plasma technology to convert that CO2 into a valuable carbon product, and really killing two birds with one stone.
Mm-hmm.
You're consuming the CO2 and you're making a valuable product that you would otherwise be using or be creating by burning fossil fuels. So that's one example of what we're looking forward to and using our plasma platform technology for.
Mm-hmm. So is that analogous then to carbon capture technologies that you see people trying to drag CO2 out of the air and just, injecting it into the rocks a mile down and hoping for the best?
Right. I would say significantly different in the sense of it isn't capture and storage.
Mm-hmm.
Because by definition, capture and storage is maintaining that CO2 as CO2 with the potential risk now in a few years, 10 years, 100 years, whether that can be converted back into CO2, at which point does it solve the real problem.
Mm-hmm.
In our case, we are taking the CO2 and converting it into a carbon product.
So it's capture and utilization as opposed to capture and storage.
Exactly right.
And the technology as it stands now, Mike, will that change? Will the Unimelt change significantly to maybe achieve some of these things that 6K Next is looking at, or will it be fundamentally the same system?
Yeah, that's a great question. I think we're trying to balance the two opposing views of like specializing the hardware equipment for a specific purpose, and on the other side trying to make a standardized product so that we're not building one-off subsystems or systems for each application. Mm-hmm. Right? The best approach would be, hey, we have this plasma technology, we can bolt on different relatively smaller subsystems for these particular end applications. So we in-house, we can make an order. The additive team can say, hey, I need 5 Unimelts to make metal powder. The core of that plasma system ideally would be just from the catalog, right? From the internal 6K catalog. Mm-hmm. And then they can add on, we need this subsystem to feed the powder, we need this subsystem to collect the powder. So we're really trying to modularize the setup and look across the company and say, in what way can we design this Unimelt and plasma system to basically get the most cost effectiveness and scalability while also hitting all of these different end applications. One interesting example of doing this is on the energy side. Across the board, we're trying to drive costs, but on the energy side, we have a particular challenge of driving cost for our first plants. And to do that, we're trying to create systems that have much more throughput than the current systems, 4x, 5x, 6x, for example. And instead of creating necessarily this really unique system, we're taking the plasma kind of module or subsystem and we're arraying that around into a reactor. So instead of designing, this unicorn, this unique thing for that particular application, we're taking what we have, what we know works well, and we're just making more of those within kind of the same domain to get the throughput that we're looking for. It somewhat remains to be seen. It's very early days on 6K Next, so it remains to be seen what exactly the equipment needs to be as embodied. But my desire would be to say to have that kind of modular mentality where we say, yep, here's the plasma system, right? We have our different subsystems and we can generate the flame that you need to then process and make the carbon, for example.
Mm-hmm. we've not had many of the hijinks stories of the old days of the being in the lab.
There was a time we were trying to extend the plasma, as far as we could to get the hottest zone, the hottest zone for the most amount of time. And we had made, in the early days, there was a lot of in-house made hardware. We would come up with an idea and we would buy the sheet metal and the components and form it and cut it and drill it ourselves. And so sheet metal is very convenient to work with. And so we made this thing called an extension tube, which is basically like a reactor within a reactor. And we used stainless steel in an oxygen containing plasma. And it turns out, and none of us had thought of this, we should have thought it through, that stainless steel is flammable at high temperatures in an oxygen atmosphere. And so we lit this extension tube or this mini reaction on fire inside of the unimelt process and just watch this thing burn and rain down metal all over our reactor. And so that was a valuable lesson learned, that we need to think these things through in detail before we run these novel experiments.
Yeah, you've learned from that one, though, yeah?
Yes. I like to think we're pretty good at thinking through our safety before we run new experiments.
Good.
Partially as a result of that one mishap.
So, Greg can set fire to metal. Mm-hmm. Mike, I believe, is stronger than quartz. Just run us through that one again, Mike.
Oh, sure. Yeah, Greg, do you remember? I don't know if you remember this, but basically when we were running the 2-inch annular torch, it happened to be just before a board meeting. We had this really long lead quartz liner outer tube with machined O-ring grooves in it. Mm-hmm. And we were down to the last one. We were trying to get results, and the thermal energy from the plasma melted the O-rings that were sealing the gases. And when we tried to remove it to do inspection, basically the O-rings didn't want to let go, and I twisted it, and the quartz broke, and the liner was no more. And we weren't able to run any more plasma until we got a new piece in, which was several weeks. So and I was pretty early into the job, so that was not a great experience, and a testament to the leadership to see through my mistake and keep me going.
Must have seen something in you that we like.
Yeah.
Well, I think just the sheer strength of him, people thinking, well, yeah, you want to fire him, you go and fire him. This guy's just snapped off a piece of quartz.
Yeah. Wow. Who wants to mess with me? I've got the sharp piece of quartz.
It's almost a rite of passage, right? Until you break something big, you're not part of the company, right? And to go back in time, this wasn't when we had 100 people or even 50 people. We were like 10, 15 people at that point in time, right? So just a testament to, if you go back in time, and Greg knows this really well. He moved into this facility that we are in today. There were 3 of them. And when I came on board a couple of years later, it had doubled, right? It was 6 people. I came in as number 7. Mike came in when we were probably around 10, 12 people. We're over 250 today.
I just wanted to put in here, one example was we had this subsystem that we're developing to increase throughput, basically increase the amount of material that we could process in a given time for the additive business. And I was working on it with some folks, and I thought we were 3-4 months away from deploying it, and Saurabh, in a meeting said, how about next week? And I kind of, looked at him like, is that a real request? And it may not have been the following week, but we deployed that and short order, and it quickly doubled the throughput based on the existing process. So I think it's one example of, really just trying to push the boundary and and asking the questions like, what would it take to be at double throughput by, within the month, for example, right?
Mm-hmm.
It's a core part of R&D and just moving things forward quickly.
I like where that story went. I thought you said you melted it by accident. I thought that's where that story was going.
Oh, we've melted plenty of other things.
When you have a 6,000 degree process, you melt a few things along the way while you optimize that hardware.
Exactly.
Yeah, I imagine it's pretty exciting though, to be faced with that, that power, basically, that energy, that power, and it's a challenge to harness it, sure, and keep everything away from it that needs to be kept away. But it must be quite an exciting prospect to go into work every day and to be dealing with that. How do you all have recollections of when you first kind of witnessed it, I guess?
Well, I've seen a lot of sparks as well, which is a good reminder that this thing is powerful, even though you can't see it. And I'm not necessarily the plasma. That of course is very powerful, and you can certainly see it. But the microwave field, right? As we all have experienced, the food gets hot in the microwave in our kitchen, and we can't see the energy, right? The waves are there, you can't necessarily see them. And so similar situation for us, and it turns out that the plasma is actually an electrical conductor. So the microwave, yes, it will couple into the gas and form the plasma and sustain the plasma, but it can also actually conduct through it and interact with other parts of the system that you don't necessarily want to be interacted with. And one example of that, again, back early days, we were trying to take temperature measurements using thermocouples, and it turns out when you put a thermocouple in the wrong spot, it being metal, in this system, you can actually start getting sparking and arcing to the thermocouple from the plasma and RF field. And I remember, it was probably 6 months in or something, and a fellow coworker set me up with this electronic box to read the temperature, and I happily went in and started taking the temperature, saw a bunch of sparks, and had to report back to the guy who helped me, like, hey, I hope your box is okay, the electrical box, but there's like smoke coming out of the box, and it's like, I think both of us knew it was fried as soon as we saw it. So yeah, definitely some unexpected outcomes here, but it's a cool system in terms of it's really multi-physics, right? You have the RF field and the microwave with the plasma and the gas flows and the thermal aspect of things and how the feedstock engages with the plasma. I mean, it's just a really rich system if you're, an engineer working on these types of things. It's really exciting.
Yeah, and I guess I'll build on that, right? And this is something that came to mind. The Unimelt is more than just the plasma system, right? As Mike described previously, that's the heart of the system. But you need the arms and legs, the other subsystems to make this work as well. And this one's an interesting anecdote. While we were developing the Unimelt system for processing metal powders, one of the aspects of that system is the exhaust, which is what happens to the gases after the powders are processed, and you get some fine material that you have to collect. So one of the subsystems that we had developed, and we actually have in production today, is a wet collection system, where we basically ensure that the gases go through a water bath so that any of the metal powders, potentially flammable, essentially get quenched, and you minimize all the safety risks associated with it. One of our first tests, we hooked up that water bath to the exhaust of the plasma system, to the exhaust of the Unimelt, and we were fairly confident it would work. So we went ahead and ran a test to see if it performed as expected, and while it was running, it worked great. The gases were flowing the right way, the pressures were being maintained, temperatures were being maintained, and then we shut the system down. And the next thing you realize when you shut the system down is the entire water bath emptied out and essentially was a nice little fountain of water back into the Unimel system, right? Basically dousing the entire chamber with water. And it took us a while to figure out because, we had people around the system looking at it, and you had a level sensor that told you how much water was there. We shut the system down, and where's the water going? And we found out the hard way when we opened the system out. We'd create a nice little puddle of water inside of the system, and then figured out, well, what happened was when you shut the plasma off, all your hot gases that were previously there have cooled down. When those gases cool down, it reduces the pressure in that closed chamber, and guess what happens? It sucks all the water back into the system. So we essentially create a nice little plasma vacuum system, and we sucked all the water back. It's one of these, that's a cool one, right? Those of us who are engineers would be like, ooh, wow, we learned something good. Let's just say the guys operating the system didn't really take too kindly because they were the ones left cleaning up the mess that we had created. So there's always that, the old adage of you learn something new every day. Yeah, in the early days of 6K, I think you learned more than a few things every single day.
Generally, though, would you say the technology has developed along the path that you expected? You must have set out with some kind of vision, back in maybe 14, 15 of where you would like to be now and what you'd like the technology to be capable of. Would you say it's kind of reached those milestones or gone above and beyond that?
Yeah, I guess looking back, Jim, the question really starts becoming, did you think this is how far we would get to on our good days or our bad days? Because we had both types of days, right? And if you ask this when we were having a bad day, which is, oh yeah, we tried everything and it's just not working, the answer is probably no way. This is far beyond what we expected to make happen. And I would venture to guess, even on our good days, right, from what we were expecting to be able to unlock with this technology, in my mind, we've already outstripped that, right? And there's two parts to that. There's the outstripped it today, but also given how much learning we've gotten to understand how much further we can take it. To me, that's the real driver that tells me, wow, this is way beyond what I was expecting or what I was hoping for, on day one.
Yeah, I can maybe add some color as far as the hardware and the technology goes. I recall distinctly really struggling, frankly, with torch stability, right? The flame, the heart of the system. That's the thing that drives everything else. And having a tough time just reproducing, saying, hey, we want this condition. Can we produce it on Tuesday and Thursday and Friday? Basically just having a nice repeatable process. And yes, it was part of the development to get to where we are, where now we do have that. But at the time, it's very daunting, right? It's you're looking at it, and especially being responsible for that system, you say, well, this is critical to what we're doing, and I can't tell folks that it will be the same from day to day. That's not a good situation to be in, right? And just, in the early days, we were sort of more, I guess, hacking, for lack of a better term, but engineering the system, right? What can we do to make this thing more stable, give it more power, etc. And so we're somewhat walking in some shadows or in the dark. And these days we're much more better with characterizing the system, building models, building predictive capability. But in those early days, it was much more challenging to try to make advancements on the subsystem. And I think we had a few key breakthroughs over time. I won't mention them specifically, but we had one key breakthrough where it basically took us from kind of randomness and non-predictability to saying, yes, I feel comfortable with this thing. It's going to work day to day, and this will unlock the ability for folks to do the downstream processing with this flame, right? That was number one. And the other one was taking that stability and then growing the power capability of it, because we didn't really know what is the ceiling on this thing, right? At the time we were running 30 or 40 kilowatts, which is 30 or 40 home microwaves, and for cost and throughput we wanted to get up to 100 kilowatts, because that was kind of the commodity industrial microwave generator systems in the market. And we said, we're leaving a lot on the table if our torch can't take this full 100 kilowatts, right? So we got to get there. And that was a big effort in the group. And, we took that learning from the initial kind of stability of the torch and applied it to this increase in power. And we were able to, relatively quickly make gains on power, going 40 to 50 to 70 to 90. And ultimately today we're running in a stable way at that full 100 kilowatts. So I've been really impressed with kind of how much we've been able to advance the core technology and make it mature enough to then enable some of these applications.
Nice. Okay, I think that's as good a place as any to draw a line under this. Thank you to the three of you for joining us today. Much appreciated. Hopefully now listeners and viewers have a full comprehensive understanding of where we are, what we're doing, how we got here, and we'll put some context for all the other conversations that are to come in the series. So thank you again. Much appreciated.
Yeah. Awesome. Thank you very much, Jim.
It was fun. Yeah,
Thank you to Saurabh, to Greg, and to Mike for participating today. Thank you for listening or watching along with us. Hopefully that has given you a sound grounding in plasma and 6K's Unimelt technology, which will come in handy if you stay tuned to the usual MANSUS channels, whether that be the 20-Minute Talks podcast or our YouTube channels, for the next 2 episodes from this MANSUS mini-series with 6K. Goodbye.